Today we're going to be talking about isosceles and equilateral triangles. So first we're going to go through some of the parts of an isosceles triangle and what makes it up. So in an isosceles triangle we have legs, which are the two congruent sides. So when you look at an isosceles triangle, the two sides that are the same length, those are called the legs. We then have a vertex angle, and that's the angle formed by the two congruent sides. So for example, if I have a isosceles triangle, and these two are my legs, they're my congruent sides, this is right here is considered my vertex angle. Alright, and then there's a base, which is the third side, this part down here. And then we have base angles, which I'm sure you can guess are the two angles that are adjacent or next to the base. So this one and this one. All right. Now with the isosceles triangle, we have a couple theorems we're going to be talking about. We have theorem 4.3, which is the isosceles triangle theorem, which states if two sides of a triangle are congruent, then the angles opposite them are congruent. So for example, we have sides AB and AC. The sides that are considered the opposite of them would be angle B and angle C. So this angle right here and this angle right here. What this theorem states is that these two angles are congruent to each other. All right, now we have a theorem that talks about the exact opposite of that. It's the converse of the isosceles triangle theorem, which states that if we have two congruent angles, then the sides will be congruent. All right. So we can use these two theorems when we're trying to discover if a triangle is in fact equivalent to another triangle, if we're trying to figure out if it's congruent during a proof. All right, so we also have a third theorem for this particular idea. We have theorem 4.5, which states the bisector of the vertex angle of an isosceles triangle is the perpendicular bisector of the base. So what's that stating is that if we take this angle right here, the vertex angle, we put a bisector in the middle, so then these two will then be congruent. All right, then we can come down and we can then say that this line, CD, is going to bisect AD. So what that's going to do is it's going to create two congruent lines, AD and DB. And because it's a perpendicular bisector, it's also creating some right angles. All right? So there's a lot you can do with this particular theorem. All right, so there's something in geometry called a corollary. And a corollary is a statement that follows immediately from a theorem. So oftentimes these are things that are in addition to the original theorem. So for example, if we look at theorem 4.3 again, which is the talking about the angles of an isosceles triangle, we actually have a corollary to theorem 4.3, which states if a triangle is equilateral, then it is equiangular. All right. So this basically just states that if all the sides are the same length, all the angles are. Same thing with the corollary to theorem 4.4. It states that if a triangle is equiangular, then it is equilateral. All right, so if all three angles are the same, then all three sides have to be the same, which makes sense. They're pretty self-explanatory and pretty obvious, you would think. All right, so here we have an example. It says copy and complete the statement. So we have if HG is congruent to HK, then angle what is congruent to angle what? Well, we can see that this falls under our theorem 4.3, which states that if the sides are congruent, then the angles opposite them are congruent. So we could say angle G and angle K. All right, now it's stating if KHJ, so we have KHJ right here. I'll erase the ones from the previous. Is congruent to KJH, so KJH over here. Then they're asking what sides are congruent. Well, then we can say the ones that are opposite them would be H, K, and K, J. All right. All right, and then last but not least, we have example 3, which says, find the values of x and y in the diagram. So we want to find x and y. So we can actually use these theorems to figure this out. Well, we can look at this small triangle here, this KNL, and we can immediately see that all three angles are congruent. And according to our corollary to theorem 4.3 and 4.4, it states that if the angles are the same, are equilateral or equiangular, then these sides are equilateral. So I can say right now, because this side is 4, that this side right here, y, is going to equal 4. All right. Now with that, I can say, all right, well, I have x plus 1 is this side of my LMN triangle. And by looking at it, I can see I have two equiangular um, angles here. So that means that this particular triangle is an isosceles triangle, which then means that the opposite sides, according to our theorems, then are equilateral. So I can say, well, if this side and this side is 4, then this side is 4. And if this side is congruent to this side, then I can just say x plus 1 equals 4. Subtract 1 from both sides, and I will get that x equals 3. So x equals 3, y equals 4, and we have solved the problem. All right, so we're going to be working with these particular theorems tomorrow. They may pop up in some of your proofs that you'll be working on. Just keep them in your the back of your mind, and also add them to your theorems postulates section along with your corollaries as well.